Okay, welcome back. This lecture is titled Understanding the Electromagnetic Spectrum of Light. And let's get rid of this black lettering for light with something a little more colorful. Okay, that's better. The universe is a very, very distant and complex thing to understand, and we're trapped on Earth. And to gain insight into how matter, energy, and time behave throughout the universe, we observe the universe by gathering light in telescopes. In this way, you can think of light as the central piece of data that we gather about the universe. And with the exception of a few locations in the solar system, all of the information we know about the universe, all of galaxies, stars, gas and dust clouds, everything has come to us through the messenger of light. You'll often hear people describe or use the name electromagnetic radiation. That phrasing, electromagnetic radiation, is just a more, if you will, fancy label for the phenomenon known as light. And we're going to investigate light's properties in this lecture. You also see in this slide the word spectrum. For the sake of this lecture and most of this class, it's useful to think of the idea of spectrum as a range of the different wavelengths of light or energies of light. All right, so the next thing I'd like to do is start to explore these different properties of light. And in doing this, I'm going to provide first an image of all of the different types of light. And these different types of light, they all have different names, and as we'll find out, they all have different properties too. So let's just start off with their names. You have gamma, X-ray, ultraviolet, visible, and visible is the part that your detector is sensitive to, your eye. There's also infrared, microwave, and radio. So these different types of light all have properties that are worth investigating. For instance, they have a wavelength associated with them, they have a frequency associated with them, and they have an energy associated with them. Gamma rays are the wavelength of light that is shortest. Gamma rays have the highest energy or greatest energy, and they have the highest frequency. And I'm going to bring in another little part of this representation now. And so you can see in this drawing a symbol of light appearing like a wave, with the waves packed closest together at the end of the spectrum where gamma rays are. And then you can also see that at the other end of the spectrum, where radio exists, the waves are much more spread out. So again, we would say that the gamma rays have the shortest wavelength, or the distance between two consecutive peaks is the shortest. Also, gamma rays go through a complete oscillation very quickly, so we often would say they have a high frequency. I probably won't use the word frequency too much throughout the semester, so you can not pay too much attention to that, but I will definitely be talking about energy. So gamma rays have the shortest wavelength and the highest energy. At the other end of the spectrum, we have radio. And radio has the longest wavelength. It also has the lowest energy and the lowest frequency. So the waves are very spread out. The radio light does not have much energy compared to the other wavelengths of light.
Okay, to help you start reasoning about these properties of wavelength and energy a little better, I'm going to identify an area in the infrared portion of the spectrum of light, and I'm going to go down to this representation that is this wiggly line that is supposed to represent how light travels as a wave. And it turns out that the wavelength can be identified on this representation by drawing a line from the height of the peak of the wave at one location to the next consecutive peak or height of the wave at its maximum. And this is the wavelength of the light. So I'm going to do that in the infrared section, where I put my first line at the peak at one point in infrared, and then I go over to the next place while still in the infrared where the peak happens again. And that is literally a distance. That is how far light would have traveled during one oscillation. And that idea of how far light travels during one oscillation is the wavelength of that light. So we can see that as infrared light were traveling through space, it would travel a certain distance, identified here by this wavelength using the symbol lambda. And I'm going to go over and identify a similar wavelength of light, but now in the X-ray part of the spectrum of light. So if I go over here into X-ray and I identify one peak or crest of light, and I go and I find another consecutive crest or peak of light in X-ray, and I draw the line, that is literally how far an X-ray would have traveled during one oscillation as a wave traveling through space. So that's the wavelength of X-ray light. Now you don't have to worry too much about this idea that a wavelength is the distance light travels during one oscillation. I just wanted to bring that up so that you understood why I was marking it from one crest to the next. So we can see in this image then that an infrared wave has a longer wavelength than an X-ray wave of light. And we'd also say that the infrared light has lower energy than the X-ray light. So this becomes a useful representation, looking at light as a wave and identifying its wavelength. And I just want to introduce another piece of terminology. It's often convenient not to think about light as a wave traveling through space, but rather to think about it as a little ball of energy, if you will, a small unit of energy that is light. And when we think of light that way, we introduce a new term called photon. So a photon is a small unit or bundle or particle, if you will, of light. So an infrared photon has much less energy than an X-ray photon. In the same way, a radio photon has the least amount of energy of all forms of light, and a gamma ray photons are the most energetic forms of light. And if you look in the middle of this representation where it says visible at the little rainbow, we could even talk about just visible light for a moment and say that red light has the longest wavelength and has the least energy of all of the light that our eye is sensitive to that we call visible, while blue light and indigo and violet light are the part of the visible part of the light spectrum that we can see with our eye that has the greatest energy and the shortest wavelength. So I'm going to use the words photon, wavelength, and energy quite a bit moving forward from here, and I just wanted to make sure that we had said all those terms before I move on to the next slide. So I think it'd be a good idea at this point that we check to make sure that you're understanding how to compare the different properties of light. So what I'll do is first on the left-hand side here, I'm going to make a little wiggle to represent some red light, and I'll list its properties as wavelength, frequency, energy, and speed. And then I'll, on the right, draw some blue light and list its properties. And then what I want you to start thinking about is how do these properties of light, wavelength, frequency, energy, and speed, compare between red photons and red waves of light versus blue photons or blue waves of light. And so I will introduce the less than, greater than, or equal to symbol here. And I want you now to take some time and think about which of these symbols should go between the comparisons of the properties of the red light versus the blue light. So take some time and think about your ideas, and we'll check back in a second here and think about how you would explain the relationship between wavelength, frequency, and energy to your partner who might be struggling with this. Okay, just to review, if you go back and look at the properties of light in that graphic from earlier, you'd see that red visible light has a longer wavelength or a greater wavelength. You'd see that blue light has a much higher frequency, so higher frequency or more frequency, and the energy of blue light or blue photons is greater than red photons. But both of them are light, and so both of them travel at the speed of light, so the speed comparison is equal. And the letter C is given to represent the speed of light. That isn't something that we'll see much of or talk too much about over the semester. I just wanted to make sure that we all understood that all wavelengths of light, all forms of light from gamma to radio, all travel at the speed of light, so their speeds are all equal. Okay, in the next section, I'd like to start to connect the idea of what kind of light an object gives off with another physical characteristic of the object, and that's its temperature. So first I'm going to draw a blue object, and I'm going to indicate that there's a bunch of high energy blue photons coming out of it by these wiggles with short wavelengths. So they're high energy, short wavelength blue light coming out of the blue object. And then I'll draw this other red object and show that it has a bunch of low energy, long wavelength red photons coming out of it. And so the general rule is that an object that has many or mostly high energy, short wavelength light or photons coming out of it will be hot as compared to an object that gives off mainly or mostly low energy, long wavelength light or photons, and that object we would consider to be much cooler. So to recap, we have the blue object that gives off mostly high energy, short wavelength light or photons, and that object would be hot. And then we have this red object, which gives off mostly low energy, long wavelength photons or light, and that object would be cool. I want to define another quantity that's going to be really important to our understanding of objects in astronomy, and that quantity relates to how much energy is flowing out of an object every second. It has a technical name. That name is luminosity, and we use the letter L for luminosity, and again it's the total amount of energy that is given off by an object every second. Luminosity depends on both the surface area of the object and the object's temperature. So again, luminosity is the energy output of an object every second, and if an object becomes much larger in area, its luminosity can increase, and if the object becomes much hotter, its luminosity can increase. So as a general way of thinking about luminosity, we could say that big and hot objects have a greater luminosity than small and cool objects. So this larger blue object has a high luminosity or a large luminosity or is giving off a lot of energy, and this smaller red object giving off red photons is much cooler and smaller and therefore has a lower luminosity or a smaller luminosity or is giving off less energy. So if we were going to compare the luminosity of the blue object to the luminosity of the red object, which of the symbols less than, greater than, or equal should go into that spot? And the answer is that the luminosity of the blue object is greater than the luminosity of the red object. Okay, now I have a situation I want you to consider in which you have on the left side, a medium-sized red object, and next to it, a small, medium, and large-sized blue object. Then on the right side, you have a medium-sized blue object, and next to it, a small, medium, and large red object. And what I want you to think about is which of the blue objects on the left side would you have to pick to have the luminosity of the red object be equal to one of those three blue objects? And the same on the right side, I want you to think about which of the red objects would you have to pick for the luminosity of the blue object on the right side to be equal to those red objects next to it, the small, medium, and large objects. So on the left side, we have that the medium-sized red object would be giving off a certain amount of energy based on its size and temperature. And if we compare it to the largest of the three blue objects drawn next to it, we'd find that that largest object is both hotter than the red object and larger than the red object. So it would definitely be giving off quite a bit more energy and have a much greater luminosity than the red object. Now the middle-sized blue object is about the same size as the red object. So even that blue object would be giving off more energy than the red object because it is the same size but hotter, and therefore would have a greater luminosity. The very small blue object very well could have the same luminosity or energy output as the medium-sized red object, because even though it's smaller, it's also hotter, and therefore with its greater temperature, it could give off the same amount of energy as the red object, even though it's smaller than the red object. Its greater temperature could cause it to have a equal luminosity to the red object. On the right side, we have a medium-sized blue object, and that medium-sized blue object would certainly be giving off more energy than the smallest of the red dots, or the red objects. And if we compare again the medium-sized blue object to the medium-sized red object, we have two things that are the same size, but the blue object is hotter and therefore has a greater luminosity. Now when we get to the large red object, we would find that perhaps this large red object, even though it's cooler than the blue object, is much, much larger. And that greater size would allow the large red object to have a luminosity that might be equal to the blue medium-sized object. And on the left side, we have that the medium-sized red object would have the same luminosity as the small blue object. And on the right side, we have that the medium-sized blue object would have the same luminosity as the large red object. So the next thing that I want to do is start looking at the different ways we can represent the luminosity, area, and temperature of objects. And the first thing we're going to do is draw a graph. And this graph is going to be something that we examine quite a bit over the next couple weeks. And the vertical axis of this graph is going to be labeled with an L to stand for luminosity. And I want you to notice that as you move further and further up this vertical or up and down axis, things will become brighter and brighter, or give off more and more energy, or have a greater and greater luminosity. And along the sideways or horizontal axis, we have temperature. And this is a really important thing to notice, that the hotter objects on this temperature scale are near the origin, or on the left side, and the cooler an object is, it'll be represented further out on the right side of this axis. So as the axis moves outward, it's getting cooler and cooler. And I'm going to identify 3 objects with the letters A, B, and C on this graph. And so their temperature and luminosity are defined by the point where they are on this graph. And what I want you to do is I want you to think about how you would compare the luminosity and temperature of A, B, and C to each other. And so I'm going to list here all of the different comparisons. And I want you to think about, which of them is less than, greater than, or equal to the other. So you're going to fill in each of those spots that comparison. Okay, so take some time and think about your answer to those comparisons, and also think about how you would explain your answers and your reasoning for your answers with your partner. Take a look at the graph and think about where those different locations for A, B, and C are located, and how you'd explain how to read the graph and make those comparisons from the graph. And we'll check back in just a second. Okay, I'd like to work through these comparisons that we were making for objects A, B, and C. The first comparison for the luminosity of A versus the luminosity of B. These two objects are aligned horizontally, so they will intersect the luminosity axis at the same location, so they have the same luminosity. If now we compare the temperature of A to the temperature of B, what we find is that object A would intersect the temperature axis at a much hotter value than B, so A is hotter than B. If we compare the luminosity of A to the luminosity of C, we see that A is much higher up on the luminosity axis, indicating that it gives off much more energy. So the luminosity of A is greater than the luminosity of C. If we compare the temperature of A to the temperature of C, we see that these two objects are aligned vertically, so they intersect the temperature axis at the same location. So the temperature of A is equal to the temperature of C. If we compare the luminosity of C to the luminosity of B, we find that B is much further up on the luminosity axis than C, so it's giving off much more energy. So the luminosity of B is much greater than the luminosity of C. And the last case is that the comparison of temperatures for C and B, where we would find that the temperature of C intersects the temperature axis at a much hotter temperature than the temperature of B. So the temperature of C is much greater than the temperature of B. And with that, we'll move on to the next piece of information. So now I'd like us to consider these same 3 objects A, B, and C, and I want you to think about your answer to these 2 questions. Which object is cool but gives off a lot of energy? And which object is hot but gives off very little energy? So I want you to think about your answer to this question. And then I also want you to think about how you would explain your answer to somebody else in the class in terms of the ideas of luminosity and temperature and where these locations are on the graph for A, B, and C. And we'll check back in just a second. Okay, for the first question, we're looking for an object that is cool but gives off a lot of energy. And the cool objects, according to the temperature axis, are things on this graph that would be far to the right. And as far as things that are giving off a lot of energy, those are things with a great or high luminosity. So we look for things towards the top of the graph. And so something that is to the right and at the top of the graph would be object B. For the second question, which object is hot but gives off very little energy? Something that is hot would be on the temperature axis to the left. And an object that gives off very little energy will be low down on the luminosity axis, so near the bottom of the graph. And so something that is giving off very little energy, low luminosity, but is hot to the left on the temperature axis would be object C. All right, so as the last thing we're going to talk about in this video, we want to start relating the idea of luminosity to both temperature and area. So we might want to consider whether these objects are big or small. And so for the object which is hot but gives off very little energy, C, is that object big or small? And what about the object that is cool but gives off a great deal of energy, like object B? Is that object big or small? All right, so what we'll do then to try to think about area is to rank the size of objects A, B, and C, their surface area, from smallest to largest. And when we come back to class next time, we'll start thinking about that ranking a little more.